morning, everyone. Thanks for joining us. I have a couple folks still signing on. There we go. All right, thanks for joining us for the first part of the Optimizing Hybrid Heating Systems webinar. We'll get started right away so we can take advantage of the full 90 minutes together. So my name is Jenna. I work as a Built Environment Initiatives Coordinator with the Community Energy Association. I'm going to give a quick introduction before I pass things over to Rob Hope with Ecolite and Energy Solutions for his presentation introducing hybrid heating systems. At the end of the webinar, we're just going to wrap up with a quick poll, which gives you the opportunity to provide any feedback and suggestions for webinar topics we should explore next time. Perfect. So I'm joining you today from the traditional territories of the Snaiks Nation, the Silks Nation, and the Ktunaxa Nation, and what is now known as Nelson. And I'd just like to express my deep respect and gratitude for their generations of stewardship of these waters, forests, and mountains. In an effort to center Indigenous stories and voices, I'm opening this webinar highlighting Indigenous leadership in the built environment. So if you just click forward there, Rob, please. So highlighting some of the work that the Penticton Indian Band, one of the 7 communities of the Okanagan Nation, has been doing. They've been showcasing incredible leadership in the high performance building space. So an example of this is the construction of the new Little Paws Child Care Center, an 8,600 square foot child care building with a very insulated building envelope, triple glazed windows, and a high efficiency heating system to provide comfortable interior conditions all season long. So with these features and the addition of solar panels, the building would be energy self-sufficient and will provide a safe and healthy place for generations to come. So for more information about this project and others, you can visit pib.ca. Just forward one more slide there, please, Rob. Perfect. So who are we? The Community Energy Association. We are a registered charity and nonprofit committed to accelerating bold action by local governments and Indigenous communities related to climate and energy. So we're the only nonprofit in BC focused exclusively on supporting local government and Indigenous communities on climate and energy. We have 50 staff located across 27 communities and 5 provinces and territories. So we accelerate local action on climate and energy through our collective capacity, expertise, experience, passion, and commitment to truth and reconciliation. So what does that have to do with building better? Well, CEA's work recognizes that the built environment is a main source of community-based greenhouse gas emissions, and that action in these sectors can not only result in significant greenhouse gas emission reductions, but can lead to enhanced community resilience and energy security while increasing the comfort, health, and safety of our homes. And just the next slide there, please, Rob. So today's webinar is an initiative through the Kootenay Clean Energy Transition. So KCET is a project designed to respond to changes in energy efficiency, renewable energy, and home comfort space. So through KCET, we aim to assist Kootenay and boundary communities in preparing for a more energy efficient and healthy future by providing training and capacity building sessions like this one. So thanks to the generous support from the organizations listed at the bottom of the slide, we're able to offer this workshop for free as part of that initiative. And then to see a list of upcoming workshops and webinars, make sure to visit our webpage at communityenergy.ca/news-events. And there you can also sign up for our high performance building newsletter. It comes out every 2 months to highlight news and events around new builds and retrofits across BC. And the next slide there. And then just a quick little information on the Home Performance Contractors Network. So for those of you on this call who are doing home energy retrofits, I just wanted to introduce this network. If you're doing heat pump installs, window and door retrofits, or insulation upgrades, and your clients are wanting to access provincial and utility rebates, this is the network for you to join. Becoming a member involves industry-specific training, and then upon completion of the training, you receive training subsidies and costs back for those courses. So if you have any questions about the Home Performance Contractors Network, you can reach out to them directly using the info@ email address just listed on the slide there. All right, and one last slide just for some housekeeping items. So CEA, we're dedicated to offering educational opportunities to all, no matter their current knowledge or experience level. We prioritize creating a safe space and welcoming environment for attendees to engage and participate. So this slide outlines some guidelines we ask everyone to follow over the course of the next 90 minutes. But above all, just please show respect to our speaker and fellow attendees, and feel free to ask any questions you may have. We're happy to address them. All right, so just a couple more things before I pass things over to Rob. If you have questions as we go through the presentation, feel free to raise your hand and we'll call on you to unmute, or you can put your questions directly in the chat and I'll do my best to ask Rob if it's relevant to his presentation at that time. We'll also save questions till the end of the last kind of half hour of our session today we have for questions from you folks. You'll notice as you signed on today that the session's being recorded. It will be shared out with all registrants and be posted to CEA's Built Environment webpage for public viewing. For those of you collecting continuing professional development points through BC Housing, we will be sending out confirmation of attendance emails to those of you who were on for the full duration of today's webinar. All right, so that's it. It's with great pleasure that I introduce Rob Hope, Senior Consultant with Ecolite and Energy Solutions. For those of you who haven't joined us for a webinar with Rob, you're in for a treat. Rob has decades of experience in the HVAC industry, and we're really lucky to have him here with us today to share some of his knowledge. So with that, I'll pass things over to you, Rob.
Thanks, Jenna. And thanks everybody for taking the time to attend. Here's the agenda for today. We're going to be talking about dual fuel or hybrid heating systems. So we're going to start with an understanding of what that actually means, followed by quality installation fundamentals. The big part of the quality installation fundamentals will be the importance of pre-change-out procedures, and that will be followed by right-sizing equipment, balance points, and controls. I wouldn't get too concerned about the language. It'll become apparent what we're talking about as we go, and then we'll follow up with questions. And as Jenna mentioned, I'm very happy to take questions along the way. You even turn it into a conversation as we go. It's fine with me. So a dual fuel hybrid heating system typically combines an electric heat pump with a gas furnace. One of the biggest features is that your gas furnace is going to actually take over when that heat pump isn't able to keep up anymore. That's the point of having a dual fuel system. As the outdoor temperature goes down, the heating capacity of the heat pump also diminishes, its efficiency diminishes, and then at some point, what we call a balance point, your gas furnace takes over. Optimizing the performance of a dual fuel heating system depends on a few things. I think it's intuitive to understand that you got to size things properly, you got to install things well, and you got to commission things thoroughly. That's the key three acts of the play that plays out when you're installing the system from beginning to end. The reason we're even here talking about this is because unfortunately, we don't have an environment of enforced, understood, accepted standards of practice in the Part 9 world, in the housing part of construction or retrofits, right? So it's kind of, a bit of a frontier there. And so consequently, we have a high failure rate, not just in terms of efficiency, of functionality, of meeting performance generally, but also just comfort expectations even. So what we're going to do is talk about how to avoid those kinds of things from happening. And that includes the fundamentals. What we're going to start with this particular session is pre-change out. Before you take out the existing system, what you should consider, the things you need to do, the processes you should go through, and the calculations and diligence that has to come with that. That's today's session. And then in November, we're going to the next step. What is an installation? What's the difference between a good and poorly installed system, and how to make it a good installation, and a critical thing is, once everything's done, how to commission, test it all, work all the bugs out, shake the system down, and have it ready for handover to the homeowner. So let's get started with part one. There's three critical general categories that we consider pre-change out procedures. There's the homeowner interview, We'll go into each of these in the next few slides. There's how the home is performing. Is it an old leaky, drafty house that poor insulation, or is it relatively tight with good insulation? Who knows? These are one of the things that we got to check out. And what is the existing ductwork that you're going to be changing into that's going to still be there when you put new equipment in? How is that going to either hinder or help your decisions when you put in a new system? We have to do our diligence on a technical review of the existing equipment, ducting work mostly. So the discovery is exactly what it implies. We want to discover stuff, right? Whenever I've done this, and I've done this many times, I've been doing this business all my life since the mid-70s, and a long part of that was doing retrofits myself. And one of the greatest insights you can get is just simply talking to the homeowners. How's this system working? And then they'll tell you, I got cold spots over here, hot spots over there, too loud over here, and down the hall I hear a bang in the wall. They'll give you insights that are hard to find by just testing, right? And it's their experience that you want to improve anyway. So it's good to get as much insight from the homeowner as possible. That's part of it. And also their expectations. Why are you changing this? It could be as simple as, well, that one's broken, I need a new one. But in most cases, there's a bigger picture involved. There's incentives, rebates. They want to take advantage. Now's the time they're thinking about upgrading their windows or insulation. And so they're doing this as part of a bigger picture, right? And that's important to understand. What's the motivations? And also, it's pretty important to understand what their expectations are. How big is that thing going to be? Where's it going to sit outside? How's the lines get into the house? How noisy is it? All those kinds of things, right? So expectations are pretty critical because, as you know, anybody can zoom anything these days, right? And you can equip yourself pretty dangerously with just not enough complete information. So part of your job is to protect the homeowner from themselves, right? As a contractor. So that's what I think anyways, to make sure that what their expectations are aligns with what's actually possible and their budget. Once we get that done, we come to what I consider an understanding with the homeowner. Why we're there, what the expectations are, and all that kind of stuff. Then we do the technical stuff, right? We don't want to guess with the performance of the house itself, because heating system, I'm sure you've all heard this a million times. It's always worth saying that the house, the heating system, everything in it, the people in it, how it's used, it's all one holistic system, really, right? And so we don't want to fragment the mechanicals from the building itself. We want them to work together. So we want to know how the house performs. Is it poorly insulated? Is it leaky, or is it well insulated? Has there been improvements, upgrades to the windows, for example, since it's been built, and that kind of stuff. And one of the ways to do that is to do a blower door test and an inner-guide assessment valuation. Now, often for mechanical contractors, this has already been done. This is one of those areas of this whole procedure that tends to get fragmented. It doesn't have to be that way. Where an energy advisor has already been there, they've done their evaluation, created a report. Contractor comes and doesn't often even ask for that. But if it's been done, it's a pretty critical thing to know, because what that tells you is a few things. One is, generally speaking, what the load of the house is, not precisely. it tells you the kinds of systems that were discussed, and whether it's a hybrid system or it's a full electric system or not, for example. It basically does, as it says right here, gives a better understanding of the existing home performance. What kind of system or home are you putting the system into, right? And how does that affect your choice of the system itself is pretty important to know. It also does what's called a energy model. And we have to be very careful. The energy model is modeling the energy performance of the building. It is absolutely not a load calculation. It is not the heat loss and heat gain. It's just the energy performance. The heat loss and heat gain still has to be done. But you can use the information from evaluation that the energy advisor did on the HOT 2000 report. So as you can imagine, the energy advisor has to put in all the known factors, the air change rate, the window values, the R values in the walls, and so on and so forth, all the assembly details. And as I said, it does not constitute a proper verifiable load calculation that complies with the standard. The standard is F280-12. However, you can do two things. You can either take the information from the energy model and upload it to a program called VoltaSnap, which is an accredited, verified program that does change all those numbers into a proper F280-12 compliant load calculation. Now it's done. All that would take is a little coordination with the energy advisor. The other way is if you're contracting, you'd rather do your own, then what you can do is take the information from the energy advisor, all those building assembly details we just talked about, and input them into your own program. There's a few that are F280-12 compliant, and come up with your own set of load calculations for both heat loss and heat gain. That would be an F280-12. There's a few programs that do that. I think this is later on in the slides. Let's see here. We'll get to them later. But there's a handful of programs that any HVAC contractor, anyone, period, has access to that you can use to do proper load calculations.
Hi, Rob. A quick question about VoltaSnap. There's just a comment in the chat that it was only good for whole house calculations, not room by room. Could you speak to that?
Well, if we're doing retrofits, we only need a whole house calculation. But otherwise, if it's a room by room that you're looking for, then the first model has to be done in room by room, which is a different mode, right? And it's typically pretty rare to see. So in that case, then you would take the assemblies and break them up room by room. So you would have to do the room by room, but that is not a typical circumstance in a retrofit. Sometimes it's necessary, but not very often, because you have an existing set. It's not like you can manipulate ducting completely. You'd have to tear walls open and all that. That becomes more than just a retrofit. That is now a renovation, really. And a renovation and a new construction are very similar in process and procedure. And so you would want to have a proper load room by room load calculation done. You still need your energy evaluation, right? But for the purposes of sizing your mechanical equipment, you need to do a room by room. And in a house where you're not going to be changing the existing ductwork system, opening up walls and ceilings, block load is 90 point something % of the time adequate.
The Rob, sorry, I'll just jump in super quickly. The only thing I would add on Tom's comment there, which is a bit of a detailed nuance, is that VoltaSnap is only verified in terms of F280 verification for whole home calculations. It's not verified for room by room. So it can only be used for whole home.
Yeah.
Great, thank you.
Okay. So one of the biggest issues that any contractor is going to face is, you got whatever, some sort of furnace in there, and it's attached to ductwork, and that ductwork disappears outside of the mechanical room and is hidden now in walls and ceilings all over the place, right? What you can't know for sure without checking, testing, and evaluating is, whether that ductwork is appropriate for the proposed new system, whatever is being considered, whatever you have in mind or have already determined you're going to put in to replace that existing system. That ducting has to be able to adequately deliver the energy of the new system. And that is usually where the problem lies, especially if you're going from an oversized gas furnace to a hybrid system. Now you got extra resistance, you've got very lower tolerances for airflow and all that kind of stuff, more potential pressure drop. There's a whole bunch of potential issues that you need to work out before you commit to the new system. The biggest of that is airflow. And there's an easy way to do it. You can just get, it's not expensive. It's a tool, basically. It's a grid that goes into the ducting of the existing system. You run it and you have a gauge. It measures the pressure before and after the filter, for example, and it tells you, okay, you got this much airflow, this much static pressure. That means you're good for 3 tons or good for 4 tons or whatever it is. Now you know. Now you know. Now you know what your limitations are or your opportunities are. You can't really, if you don't do the static pressure testing one way or another to find out what the static pressure drop of the existing ducting system is, you're guessing, right? Then what you are counting on is, coincidence, good luck. That's all going to work. This is where the problems happen most often. Is you get a call, this isn't working, just had to put in, and you go there and you realize, okay, there's a 4-ton system installed into a 3-ton ducting, and the coil's freezing and they're not getting adequate cooling, adequate heating, or whatever. That's very often the issue. So diligence, testing, get the equipment. Every contractor should have this in their bag, just like having a screwdriver, right? You wouldn't show up to you wouldn't call yourself a contractor if you didn't have some tools. And this is one of the tools that every contractor should have. The airflow impacts the size and performance of the heat pump. So these notes here, we've just gone over some of those. Centrally ducted heat pumps need higher airflow. We need to ensure ducts can handle the size of the system installed. Coils also need certain minimum of airflow going across it. And airflow can play a role in dehumidification. How fast that air is going across a cold coil will determine how fast or how slow the latent heat in the air gets condensed and dries up. So diligence, a little bit of calculating, measuring. This is kind of what it looks like, right? You're putting a probe in on 2 sides of the coil, on the return side, on the supply side, right? You're doing it before and after the filter. You've got your gauge reading the flows and pressures and all that kind of stuff. On the right here, you've got the grid. Usually that just goes straight into your return air. You pull up the filter and you stick this in place of the filter, and it measures the airflow across multiple points. So you get an accurate reading. And some of the kinds of readings you get, here's an example. So in this case here, test 1, all grills open. Static pressure measured in the return 1.74, and in the supply 0.156. This is an inches water column, airflow at 992 cubic feet per minute. Total ductwork pressure loss, that's the total external static pressure, is 0.33 inches water column. You can see on this chart below here, you know, your 992 CFM at 0.33 goes up to more CFM if you have higher pressure. Obviously, that means higher velocity as well. There is a dance you have to do between velocity and pressure, so that you're not, you know, creating excess noise. In this case here, it says that we have the ability to put in 4 tons, 48,000 BTUs. Who cares? What matters is you do this and it tells you what you're capable of. Imagine if, you know, you wanted to put in a 4-ton system and you did all this work and says, wait a minute, you really only have enough for 3 tons. Then you've got to decide, okay, I only got 3 tons worth of ductwork. How am I going to make up the rest? And then you go to your next set of options. You know, you can do things too small duct. You can add runs where duct is accessible. That's almost always in the mechanical room. You can put a return air right off the mech room plenum into a wall in the hallway in the basement, for example, is one way. You can create a dump zone. There's a few things you can do if you know what you're doing, sheet metal wise, to mitigate the condition of having too small a ductwork. Or you put in a smaller heat pump with more auxiliary heat. So really pivotal points here, right? This kind of information really puts you in one or another direction of how you need to go. So it's important to do that. Right sizing. Yeah, I guess the alternative to right sizing is wrong sizing, right? Unfortunately, that's pretty common. Right sizing is simply using popular or common, tested, and compliant software methodologies. It's not just one software. There's a number of them, as I said before. But it's the methodology that's been tested and approved and tested and approved by peer review committees all over this country, over and over again, and has the real life data that comes from having installed systems with using this methodology for decades now, right? It works. It's called CSAF 28012. It's actually required. It's in the building code, section 9.33.5. Using it, make sure that, you know, you're going to size the system appropriately, which ensures comfort. The tendency has always been to oversize systems, which, you know, creates a lot of issues. One of those issues is, what's the point? Why oversize it? That's going to cost more money than it needs to, and create a whole bunch of other issues, short cycling, shorter life cycle, and all that kind of stuff. So why spend the extra money? It makes no sense. Using F280 ensures you comply with code, so it protects your professional and financial liability that way. It reduces your liability risks. There's really no downside to using this, only upsides. In the industry right now, and this is changing. A few years ago, this was more accurate. This is changing now. Common practice, that being the rule of thumb calculations. It still happens. It happens far, far, far too often. Right? But jurisdiction by jurisdiction, Generally speaking, the industry is saying, well, we've had enough of that. We're going to start making people do these load calculations, and that's rolling out and rolling out and rolling out as we speak. And has changed to the better over the last few years, but still, it is still a very common practice just to size things by, looking at the rating plate of what was there, matching it, or just, last time we did a house like this, it was this size, and doing a rule of thumb. Less common practice is using HOT 2000 modeling from an energy advisor, and referring to these calculations for sizing equipment. So the energy advisor says, well, the modeling says the house has a 3-ton or 36,000 BTU heat loss, right? And so the contractor will at least have some guideline to go by. And the least common practice, but the good news is it's becoming more common, is full consultations with load calculations. That's full consultations means, among other things, there's a coordination with the EA, the energy advisor, with the homeowner. Somebody's measuring something using actual data, doing a blower door test, and doing the load calculations, and using those load calculations to come up with options, cost benefits, that kind of stuff. Upfront costs, operating costs, life cycle costs, all that automatically populates the pages once you've done the load calculations. It's not a lot of work to do that kind of stuff. This is the best practice, these two. We alluded to earlier the difference between a block load and a room by room load calculation. So block load, even in new construction, that's what is how a building is measured for its energy performance. It's the whole building. And an energy performance evaluation, it's not concerned with how the living room is versus, bedroom number 2 and so on. It's the building. The building itself is what matters. How is that building performing from an energy perspective is what an energy evaluation wants to know. So that's why the block load makes perfect sense. But if you're designing a mechanical system, that's not good enough. In new construction or a renovation, anything beyond a simple retrofit, you need a room by room. Room by room calculation is kind of standard practice with F28012. Whichever program you're using to do it, room by room is kind of the default that you go to do a load calculation, whether it's for your heat loss or heat gain. Here we go. Here's some of the programs. Now, just to put this in context, so there was a time, and we were involved in this, where we, were given a whole pile of programs out there claiming to be heat loss programs, all different kinds of them, F280 and non-F280 that were on the market and being used. And we did, a number of houses, I can't remember how many, and we did the exact same process with each of these programs, and the results were all over the place. It was useless, right? So this F280 standard, then, we got a lot more serious. Okay, it was got to follow a standard, and then we had programs that were F280-12 compliant. And for the longest time, there was a few programs. They were the ones you could use if they were F280-12 compliant. However, we started to notice there's actual discrepancies in those between them. So we took model homes, the heat loss and heat gains of which we've known about forever. They were the baselines. And then we measured them all against that, and we found where all the discrepancies were. We went to the manufacturers of these programs and said, here you go. Here's the data. Here's where you guys are out and in and on all that kind of stuff. Fix it. And they did. It's been tested. And now we have these solid programs that actually align with each other on their outputs. And TECA is one of them, right? SOP is another, ECAT is another. Volta Snap is another. These were verified by HVAC Designers Canada through NRCan and CSA, Canadian Standards Association.
Hey, Rob, we just have a quick question about F280 load calculations. Are you required to take a course to provide F280 load calculations?
I don't think so. Courses are available with TECA. They will provide courses with other programs like RightSoft, ECAD. It's a learning curve. Anybody can buy the software and the licenses for keeping it up to date, and then you're on your own. I think we are moving towards a certification with HVAC Designers Canada. I don't know if Ryan's still on the line, but HVAC Designers of Canada is moving towards defining, first of all, what is a design, or what is a design? And if you're doing load calculations, have you been tested and certified, so that it becomes easier for authorities having jurisdiction to verify. All you need is a certification. Yeah, they're certified. They were trained and tested, certified, and their number or stamp or whatever is on that piece of paper, so that the building officials don't have to, figure it out for themselves whether the load calculations are accurate. But at this time, you can get certified with TECA software, but not with the more commercial programs like RightSoft and ECAD.
Great, thanks, Rob. And I just put a few links in the chat. There's to the TECA and the HRAI courses around heat loss, heat gain.
Yeah, it's. I mean, the TECA one is really simple. The RightSoft and ECAD, they're a lot more complex and expensive, but they are perfect for people like Ecolink. We use RightSoft and TECA, but RightSoft is our preferred because there's a lot more to it. It's a higher learning curve, it costs more, but for us, that's what we do all day long, and it makes it worthwhile, right? So, if you're a contractor, especially, you're doing your invoicing and quotes and all that at night and working all day, you want that learning curve and that cost to be as little as possible. TECA would be the most appropriate way to go that way. And I think these days with the utilities and governments behind them, TECA software is practically, if not free, it's close to it. And the course is not that involved. So we've talked about load calculations. We absolutely need to know the loads of the buildings. We have to do that. Otherwise, we're not doing our job properly. The other thing that we absolutely have to know is the balance point if there is a heat pump involved. And the balance point is the point at which the heat pump itself is no longer able to manage the load. And that is because the starting point of all heat pumps is a nominal number, all measured at 47 degrees Fahrenheit, whatever that is, Celsius. And that's a start. If it's a 3 ton, it's a 3 ton at that number. If it's a 4 ton, it's a 4 ton at that number. But the ability of a heat pump to deliver heat in wintertime is indexed to outdoor temperature. As the outdoor temperature goes down, so does the capacity of the heat pump, traditionally, and the efficiency. And however steep that curve is will depend on the heat pump itself, the manufacturer, the top, middle, or bottom models within the manufacturer's line of equipment, and a lot of things. And the wherever that balance point is you need to switch over. If your balance point drops out, at 5 degrees Celsius, say, but your design condition is less than that for another 2-3 weeks, you need something else going on, either to help the heat pump or to replace the heat pump. In the case of a dual fuel, it'll replace the heat pump. The gas will take over. In the case of all electric, elements will come on to assist the heat pump to deliver the temperature, right? But you have no idea where that balance point is unless you do your homework and find out based on the specifications provided by either third-party agencies like AHRI or NEEP, or just the manufacturer's equipment specifications. You can see in this example here, we have A is the heating load at design condition. Let me get my banner out of the way here so I can see what I'm doing. Okay, so that's 99%. So that's design condition, right? Somewhere around 17 degrees. There it is. C is the nominal capacity, remember, at 47F of the heat pump, right? 2 ton, 3 ton, 4 ton, whatever. In this case, it's 1.5 ton heat pump, nominal capacity. But when it loses at 25 degrees, it can no longer keep up. The difference is between A and B here, this whole area here, either is all auxiliary heat. It's either 100%, or if in the case of a dual fuel, or it's at least this much in case of electric elements, all electric. You have to make up the difference after you pass this point B. But you have to keep in mind, there's no such thing as a universal balance point. We've seen it come from utilities and agencies. Change it over at 5 degrees or 2 degrees or whatever. Forget all that. That's a bunch of bureaucrats don't know what they're doing, putting numbers on a page, right? I can show you page after page after page of different manufacturers' heat pump performance curves, and they'll all be different. All of them, they'll all be different from each other, right? So you got to actually look at the equipment you're proposing to put in, whatever you're thinking about. Look at its performance curves at your design condition with your heat loss. Put those things together and say, okay, I can do this heat pump. That'll cost more money, but I don't need auxiliary heat. Or I'll do this heat pump. We'll save some money up front, but we're going to need 100% backup with a gas furnace. You can make those kinds of decisions then, right? But you got to do your calculation for the balance point, just like you do with the heat loss. Otherwise, you know nothing. You're guessing again. And here's an example. So here's a single detached home in Kamloops, 2 stories, got a crawl, partial basement, just over 3,000 square feet. It's a typical 80s house, loosey-goosey with 7.5 air changes, double pane windows at least. Won't get into too much detail, but this house, so the homeowner's in the house and they have 3 choices. I'm going to just change that heating equipment. Or wait a minute, there's grants and stuff available. Maybe what I'll do is a light upgrade to the house. Maybe I'll blow some R6D into the attic. And maybe it's time to change those windows from double to triple pane. And the third choice is, well, maybe while I'm at it, maybe I'll go the extra. I'll do the attic, I'll do, but I'll get the house really nice and airtight down to 1.5 air changes. And I'll change the insulation in the walls and the foundation walls and so on. And I'll still put the triple pane on there, right? So we have what's called the base, the light upgrade, and the deep energy upgrade. As you can imagine, each one of these gives you a different choice. As a mechanical contractor, if I have these potential pathways in front of me from the homeowner, that's going to make me want to figure out, okay, which one are we going to do? Because it's not going to be the same equipment for each of these scenarios, right? And that's really what I mean when I was talking earlier about looking at the house holistically, right? If these kinds of things are going to happen, we really do need to know about it, and we need to be a little more strategic in how we choose our equipment. So here's the results from the heating and cooling perspective. The base case is a 95,000 BTU heat loss, only 34,000 BTUs, just under 3 tons of cooling load. We do that light upgrade, it drops the heat loss by 27%. Now that's reasonably manageable, you know, with the right modulating equipment. We might be able to get away with putting something in now for a light upgrade later down the road, right? That'll work. It depends. The cooling load won't change much because it's the same exposure, same people living in the house. The only thing that really affects the cooling load is the solar heat gain coefficient on the windows, right? So the cooling load is only going to drop a little bit. But if we go into a deep energy upgrade, you're going to get that furnace replaced with the heat pump, new heat pump, maybe new furnace too, dual fuel, or maybe all electric, whatever. And one of the reasons is I'm taking advantage of that rebate. I'm getting a loan. I'm going to be here for a while, and I'm going to do all this work to this house and make it good. But I'm not going to do that right now. I'm going to do that over the next couple of years. So now we have to figure something out. You can't put in something now that can modulate 2 years from now down to 30,000 BTUs, right? Or if you can find something that does that, that's good. But the point is, you have to be strategic. You have to look how to accomplish that, right? If that commitment is there. Unless it's all happening at once, which makes it easy, then of course you go for whatever upgrade they're going to go for. That's how you determine the equipment you're going to use. In this particular case here, we have the heat load. You can see 95,000 BTUs. This is in the base case, right? We have both a standard 2-stage 5-ton heat pump and a cold climate heat pump mapped out here. The cold climate's in green. As you can see, it's a flat line. That's the benefit of cold climates. Heat pumps, they can deliver the same capacity they started with, you know, down to sub-zero temperatures. They're probably going to replace most other technologies over the next 5-10 years because it makes no sense now in our country, cold climates outside of the lower mainland, to put in anything but. And then you can see why here with a standard, even 2-stage, and there's even not single stage, 2-stage heat pump. See how fast that line drops off? Difference it makes, right? The 5-ton, both 5-ton, starting at 47F, but one delivers a lot more heat than the other. And if we use a standard heat pump, we need to make up all this pink, right? All that pink area with auxiliary heat of some sort, backup heat, whatever you want to call it. So in this case here, that would inevitably be a gas furnace, because at around 32 degrees, you're kind of tuckered out there with the heat pump, and something else is going to take over. But on the other hand, if you put in cold climate heat pump, you only need a little more than 10 kilowatts of backup to make it all electric. Whole different scenario. Everything changes. Your cost benefit changes. Your life cycle cost changes. Everything changes. The upfront costs probably go up, right? But the life cycle and operating costs go down. Either way, it's a big difference between those two options, enough that you should think about, wonder which one is a better idea. Let's flesh it out and see. And you can't do that unless you know two things: the heat loss and the balance point. we went to a light upgrade. As you can imagine, we're going, down in capacity requirement. The light upgrade, the house doesn't need as much. Still using a standard 5-ton heat pump. We still need a whole pile of auxiliary, probably forced air furnace, gas furnace, but with the light upgrade and a cold climate heat pump, we only need 3 kilowatts. 3 kilowatts of auxiliary heat is nothing, right? It's cheap, upfront cost wise. You're not going to use it very often, so it's inexpensive to operate. It becomes, now this makes a lot more sense. The higher performing houses to go to a higher performing heat pump. There's a cost benefit analysis in favor of the cold climate heat pump that's more obvious in this case here. And of course, if we go to the deep energy upgrade, it becomes even more obvious. So look here. We went down to a 4-ton heat pump from a 5-ton, but we're still dropping off quite a bit. And we still need all that pink area in auxiliary heat, right? We still need a lot of backup heat. After it gets lower than 27 degrees or 28 degrees Fahrenheit, minus 2.2 Celsius, we need something else to take over. That's with the deep energy upgrade. With cold climate heat pump, 4-ton system, it's meeting our design condition and our load condition, right here. We don't need auxiliary heat, period. It becomes optional then. Want a little backup, what's it going to do to the panel? If it's not going to be a big deal on the panel, it's not going to cost much. Yeah, why not? Or maybe we're maxed out on the panel, put in this little few extra kilowatts will push us over. Okay, forget it. We don't need it anyways, and that becomes an obvious case in point where doing your diligence, knowing your load, knowing your balance point, looking up the equipment's performance curves, putting these numbers together to see what we come up with makes a huge difference.
Hi, Rob. Just in your discussion there around the benefit of cold climate versus a standard heat pump, Katie just asks, and Katie, let me know if I misinterpreted that that's what you were referring to. But tips for having effective conversations about all the options with homeowners.
Yeah, that's a really good question, because really that's the critical point, right? That's where you're going to either convince them or not convince them to think about these things. Now, unfortunately, I'm not the greatest person to ask that, because I really, as I was saying earlier, Jenna, I kind of wing it, like it depends on the character of the homeowners. I kind of read the room. They conservative, are they numbers people, are they technical people, are they feel good people, comfort people, environmental people, and that is a bit how the style of the discussion gets determined by me, rightly or wrongly. But I think information, period, is something that you can't go wrong with, right? We need to do a load calculation. Why? Because otherwise we're guessing. It could be right size, it could be the wrong size, it could be too big, too small. If it's too big, of course, you're going to spend more money than you need to. If it's too small, you know what happens. It's not going to keep up, right? And then you got what? Nothing but problems. You got to call the contractors back. You got to get them in. Hopefully, you've got some holdback. Otherwise, you don't hear from them. That kind of stuff. You don't want the headaches, right? Get it done right in the first place. You need the load calculations. You need your balance point calculations, because otherwise, which one are you going to use? They're all different. We got to know, whether like you've got a 60 amp panel there, we got to determine whether or not we can put in auxiliary heat with electric, all electric. And for that to happen, we need to know your loads, and we need to know the balance point of the equipment, whether to go cold climate or not. we go cold climate, we probably don't have to add any load on that small panel. So let's check it out and see, right? Otherwise, what are we going to do? Guess? No, it's not a good idea. I think those are the kinds of conversations that I tend to have with homeowners. I've always found that, in not all cases, but most of the time, it's like pushing through an open door when you do that. If you have the owner's genuine interest at heart, and it's authentic, they tend to sense that, I guess, and I've seen all my life changes in the industry that have upgraded standards to some degree. We went from oil furnaces to gas, from pilot to 80% efficient to condensing, and now we're moving on beyond that. Every step along the way, every time I saw those changes, I saw the same patterns. A lot of the industry resisting and railing against the changes, and other parts of the industry saying, okay, here's an opportunity, right? And taking advantage of it. And it's no different, I think, as human nature. We're in the same situation. It's more intense. We're in a bit of a renaissance, which I wish I was 30 years younger, because it's an exciting time right now to be in this industry. And I see nothing but opportunity, lots of it. But it's, it depends on how you differentiate yourself from your competitors. And that really is how you are able to have frank, honest, thorough discussions with the homeowners, I guess. I got to tell you, this is just coming right out of my head. This is not the brightest star in the sky here. Don't forget, this is just what I think off the top of my head.
Thanks, Rob. And we have another question here just around using HRV ERVs to precondition air incoming into a conventional heat pump rather than going with a cold climate air source heat pump. So to the best of your knowledge, has any comparison analysis been done there to compare relative energy consumption? And then just a follow-up question, just asking, additionally considering HRV ERVs versus a deep energy upgrade as a vehicle to retain heat.
HRV or an ERV, just as your last few words indicated, retains heat. It doesn't create it, right? And it only retains a portion of it. It doesn't retain it all, right? You lose some. It just retains heat. It doesn't create anything. It doesn't create heat at all, unless you add something to the system. So there's no real configuration of an HRV that will eliminate the need for a cold climate heat pump. In a case where you have a house in a cold climate zone and under consideration is a standard heat pump or a cold climate heat pump, the HRV is not going to be pivotal in which way to go, and it doesn't have any effective impact on that decision at all. HRV, that house that we just showed, that case house, if they were just going to replace the heating equipment and not do no plan, there's no way they're going to do any energy upgrades to that house. What do we have? We have a house with 7.5 air changes. It's already leaking like crazy. Why do we need to spend more money introducing more air into the house? We don't need an HRV in that situation. It's pointless. It has no value, right? There's already too much air coming and going. An HRV is another leaf in the wind in that kind of situation, right? So when the house starts to get tight, that's when you really need to put in the HRVs. The upgrade going to, say, 3.5 air changes, right? A house that tight needs an HRV. Anything tighter than that, not having an HRV is insane. You have to have an HRV or ERV, depending on whether you're in a wet or dry climate. In BC, you know, we have different climates, you know, but contrary to what most people think, you know, like here in the West Coast, it's raining all the time, you know, North Shore, but we don't really have a wet climate when it matters in the summer, in which case an ERV would be a better choice, right? On the other hand, we have the Okanagan and some pretty dry climates. In those cases, an ERV is a better choice, but not by much. And then I always tell contractors, because I get the calls often, that you specified an ERV, I can't get it for another 6 months, but there's an ERV in a warehouse or a HRV in a warehouse. What happens if I take that HRV instead of waiting for the ERV? Don't worry about it. It's not going to make enough difference. It's so negligible, really. Where it matters is in the Eastern Seaboard, where I grew up in Toronto, it matters. Eastern Seaboard of the US, it matters. Montreal, it matters, but a lot more. Arizona desert, it matters, right? But in BC, it makes a bit of a difference, but not enough to worry about. ERVs and HRVs are, for all effective purposes, interchangeable. There's some difference, but it's not a big deal between one and the other.
Wonderful, thank you.
Okay, great. So one of the things that we have issues with terminology, as you can imagine, we talk to all kinds of people and people use words and we have to do one of two things, try to figure out what they're really saying or clear it up, right? So let's just get that clear. Supplemental and auxiliary heat are the same thing. Either word will do. And it is the amount of heat you need to top up what your primary heat can't do. Your heat pump topped out at a certain temperature. Now you need something to top it up, to augment it. That's supplemental or auxiliary heat, right? Backup and emergency heat. Well, it is exactly what it says. It's your system craps out, you want something to back it up. It's like a backup generator, right? It's no different. We often recommend backup and emergency heat because we design systems all over the place, remote places, all over the coastal islands, in the interior, where either it's so remote that if something goes wrong, one little easy part to fix on your primary system goes wrong, you know, your nearest contractor is hours away, getting the supplies is days away. That's when we consider emergency or backup heat to be much more critical. But if you're in a center, like anywhere in the Lower Mainland, Okanagan, you know, even in the Kootenays, you know, if you're in Nelson, you've got adequate access to contractors and suppliers, you know. It's not even a big deal for, you know, stuff to come in from Calgary if you need it to. But in more remote areas, in which there are many in BC, we always recommend having backup or emergency heat as opposed to just supplemental and auxiliary. Dual fuel heating systems have two options for switchover from the heat pump to the furnace, right? When does your furnace kick on, right? Now, ideally, that should be automatic. As a homeowner, you don't want to know, okay, you know, what's the outside temperature, or is this the time to switch it over? Is it economically the right time, or is it thermally the right time? Economic balance point, thermal balance point. Really, who cares? What should happen is you just automate it. There's not a system out there that can't be automated. And that automation can happen in two ways: set point deviation. And that is the system is saying, you know, geez, it's taking a long time to get up to temperature. They set it for this, they set it for 22, and it's been, you know, 30 minutes and it still hasn't reached that temperature. That's going to auxiliary, right? That's one way. It can be a variation of the difference in temperature. You've been away, you come home Sunday night, temperature's been set down to 17, 16 degrees Celsius, and now suddenly you want it 22. Just that alone, the difference in the temperature being that different, will bring on the auxiliary, the backup heat, right? That's one way. And then the other is just how long it takes to reach the set point. That's the simplest, easiest way for it to happen. Then there's another way to do it where you got an outdoor temperature sensor, you got a weather station, now you got a bunch of algorithms, and they're all computing and coordinating, talking to each other and coming up with okay, now's the time. That is an option. That is something that exists in plenty in big commercial applications, especially campuses, like university campuses and so on, where every tiny molecule of energy you're wasting adds up quite a bit. And so they're optimizing these kinds of systems is more critical. But in your average house, you don't need to do that. By the way, you can see on here that you have, I believe, the smart thermostats. Just a note on smart thermostats. There's a few times I've heard it now. Again, yesterday I was somewhere and the contractors, installing contractors, most that I know hate them, as I've always hated them, because they're dumb. They mess with good systems. They are not the best kind of thermostats. Smart thermostats, whatever any the utilities tell you or the province tell you, the truth is a guy could make a living going around replacing those stupid things, right? Get the thermostat that comes with the equipment. That's the best thermostat. And it's optimized. They're talking the same language. And you're not just getting an off and on switch on the mechanical side, telling the equipment, no, time to come on, time to go out. Oh, they just went out, whether it's for 20 minutes or not, turn off. Oh, they're back, turn on. That's craziness. What you need is a proper system that matches, that thermostat matches the equipment you're putting in.
Thanks, Rob. A quick question about set points there. Casper asks, if we wanted to maximize the use of the heat pump, could we just set it very low past the balance point and the system would switch over based on its internal programming? Is there a downside to this other than cost, not switching at the cost balance point?
No, there's no downside. And we're unique in BC because the cost of gas per kilowatt of heat generated at the efficiency of your typical gas appliance, which is between 90 and 96%, a condensing boiler or furnace, and the cost of a kilowatt of heat generated by a heat pump are very, 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 very close to each other, right? So working out the economic balance point in BC has no real benefit compared to doing that in other jurisdictions where the differences between the cost of electricity, the cost of hydro, and the cost of fossil fuel are starker a lot more. Then it makes sense, to understand the economical balance point. But in BC, we don't have that problem.
Thank you.
So these are the organizations. I think each home performance stakeholder council, contractor network was already mentioned. Stakeholder council was already mentioned. HRI, all of them. They all provide some sort of training. And I think when it comes to heat loss, TECA developed their own. And TECA went through the whole process of getting it qualified by Canadian Standards Association, HVAC Designers of Canada. So their program works. It's the most accessible, simple. HRAI does not have their own program. They support programs like LoopCAD and RightSoft. And HRAI is more of a national organization than TECA, which is strictly a provincial organization. But if you're an HRA member, you can take advantage of they don't just have load calculation workshops, they have many others, balance point, commissioning, you name it. And we're going to be talking a lot about that in the next session. Home Performance Stakeholder Council obviously will give you support and access to qualifications you need for rebates and incentives and that kind of stuff. So keep in mind that you're not alone. You know, you can get support. What did we learn? I'm guessing on your behalf whether you learned anything at all, but what you were supposed to is quality installation provides optimized HVAC performance, right? That includes a good combination of pre-changeout, good workmanship, and performance verification. Load calculations using F28012 supports right sizing of HVAC equipment and avoids unintended consequences that come with rule of thumb. The capacity point should be calculated in form switchover. Now, that's kind of a little bit misleading. It's right, but it's not entirely correct. The capacity point should be calculated to know what equipment even to put in. That's the critical part. The switchover, you figure that out later, right? What equipment, period, you need. You can't know that unless you do the balance point calculation. And supplemental heat and backup heater terms that should not be used interchangeably. Otherwise, the language police will come along and something will happen. It's not that big of a deal, honestly, right? I mean, it's just, it gets confusing sometimes that, you know, somebody's talking about auxiliary and another person talking about emergency. And from my point of view is, okay, which is it? Let's get that sorted out. Do we want backup and emergency, or we just want auxiliary and supplemental? Let's get that sorted out so that we're all talking the same language and we don't create potential for an issue that came from simple confusion, right? Getting the language correct is helpful. It's not critical, but it's very helpful. And that's it. The slide we've all been waiting for.
Wonderful. Thanks, Rob. I really appreciate that. I know it was a lot of information to cover. Folks, we still have some time on the call left for questions. I'm also going to run that poll. So feel free to raise your hand and we can call upon you or put them in the chat. And Rob, as folks are getting their questions together, could you just remind them what they can look forward to next time in our part 2? We're going to do a little recap of what we just talked about so that's in context, but we're going to focus on installation. What is, how do you know what's a good installation? How do you ensure that a good installation is done compared to not a good installation? And then commissioning. That's how to verify the performance of the equipment. You've done a bunch of work, you put it in, looks great. Does it work? The shakedown. There could be component failures. There's simple warranty issues. You got to now go replace a part. Or it could be something bigger, a design issue. It could be the load calculation wasn't done right or something like that. Whatever it is, you got to test the system, make sure that the manufacturer delivered to you something that works and doesn't have any inherent failures or component issues in it. And then you want to commission and test everything to make sure that you're delivering the air that you designed to deliver to where it needs to be delivered, at the temperature it needs to be delivered, at the sound decibel level it needs to be delivered, and you've met the client's expectations as best as possible. Great, thanks. And I did put the link to the next webinar registration page in the chat. I'll also include it in the follow-up email that will also house Rob's presentation slides and the link to this recording. So you had a couple questions in the chat here. Katie asks, can you talk about customer demand for dual fuel versus fully electric? Really depends on where you are. In the lower mainland, the demand for all electric is much higher than dual fuel. A number of reasons. One is that it's just pretty common to have all electric. Bigger panel sizes
generally speaking, except in the older parts of the city, and more awareness, I guess. In the interior, we have a whole different mindset, depending where you are in the interior, but most of the interior, dual fuel is the preferred way to go. And there's a lot of good reasons for that. One is access to contractors, heat pump contractors in particular, for maintenance, service, repairs, when things break down. All that is an issue. It's more difficult. I mean, we've got them all over the place in the Lower Mainland, in places like the Okanagan, especially around Kelowna. But I deal with builders and homeowners all over the place, and that's the most common complaint. I can't get a contractor. I can't get a contractor. I can't get a contractor. Right. So in those cases, dual fuel is probably a good way to go. I would, if I was in that kind of a situation. From an economic point of view, it's not. There's no black and white, which is better. It depends on a few things. The size of your existing panel is a big one, and the condition of your house. If you have a reasonably well insulated, tight house, spending an extra couple $1,000s for a cold climate heat pump reduces that cost on the panel. And you'll be paying for electricity for maybe a month, of the year straight when the auxiliary is running, in addition to your heat pump. But your overall savings, if you're not running gas for 4 months of the year, it probably breaks even. It's close enough that it's not a slam dunk one way or another. Probably the most compelling reason in the interior or elsewhere for me, if it were me, and as I see a lot of our clients do, is go for the gas dual fuel hybrid system, because it gives you a little insurance when it comes to the possibility of your heat pump having an issue.
Great, thank you. And Kim asks if you have any additional information on controls and thermostats. So you could share any additional resources.
Yeah, there's a category of product that all manufacturers have called communicating thermostats. Whether it's a Carrier or Lennox or Trane, American Standard, doesn't matter. They'll have, essentially the top tier, middle tier, and lower tier. Lower tier are like for spec houses, and that kind of stuff. That's your bargain basement product in their catalog of products. Middle tier is more budget conscious. That doesn't mean it's bad. It just means that it's a little bit better than the bottom tier. Not quite as sophisticated as the top tier, but you pay for that top tier. But what you get is what's called communicating systems. Usually a thermostat will have 2 wires that are sending a 24-volt signal back and forth, off and on, off and on, off and on, depending on the temperature in the room. But it'll usually have at least 2 other wires sending data back and forth. And that data is communicating between the thermostat and the equipment and the outdoor sensors and everything else, and optimizing, longer run times, less, making things more efficient or more comfortable. It's actually providing insight into the control of that thermostat to optimize the system. And it's using proprietary language, right? So you come along and you take that nice quality system and you put something that doesn't have proprietary language with it, doesn't have the data going back and forth, is just off and on. All the optimization that was there is reduced to a dumb off and on system. So generally speaking, there's an awful lot more to it. We could have a whole course just on this, but generally speaking, the best thermostats is the thermostats that come with the equipment, right? If it's a Lennox thermostats. If it's a Carrier thermostats, and so on. Mitsubishi, Daikin, it doesn't matter. Get the thermostats that come with the equipment. That's ideal. That's the best. And keep away from the so-called smart thermostats. They cause nothing but havoc for mechanical contractors. I know they look nice and they're cool. You can integrate them with your cell phone or whatever. But you can do that with most of the other thermostats as well. You can connect them remotely to phones, laptops, and whatnot. But anything that tries to anticipate your coming and going and all that kind of stuff, what it does is it creates too many cycles. Things are cycles that should be running, cruising, get interrupted. It's off and on and off and on. And, most people disable those functions is what I've seen. So what's the point of them? I think, they're really good at marketing directly to homeowners, whereas all other good quality thermostats aren't marketed to homeowners. They're marketed to mechanical contractors, right? And I would keep away from those if you could. Other than that, the obvious thing is in an existing home, there's a high likelihood that you have a single stage thermostat in an older home with 2 wires going to it. Do not let that be the case with the new system. You have to replace those 2-wire thermostats with 4 wires at least. You cannot put in a 2-stage anything with just 1-stage set of wires. And we see that a lot. And that's just simple laziness. Take off the thermostat on the wall, put the new thermostat on there. It's got 2 wires. We got a 1-stage thermostat therefore. Well, even if it says 2 stages on it, you only got 2 wires. Now you got a 1-stage system. That happens quite a bit. Other than that, I'm not sure what else to say about controls without going into a lot of detail.
Yeah, perfect. And Katie just put a comment in the chat that she kept her old Nest with her cold climate air source heat pump, and fully agree with what Rob is saying. She's constantly fighting it to stop changing the set points.
Yeah.
And then, sorry, there's another question here. Kim asks, do you happen to know if all heat pumps have an outdoor sensor, or high-end just look at weather from Wi-Fi?
All heat pumps have an outdoor sensor somewhere. They don't always get put in. That house I was telling you I was out yesterday, they were having issues. They didn't have an outdoor sensor. That was one of the issues. Yeah, the outdoor sensors are kind of part of the package. They just don't always get put in, but they should have. You need to have an outdoor sensor. Ideally, in a shady part of the lot, somewhere in a shady area. But usually, the default is right in the heat pump outdoor unit somewhere.
Great, thank you. Could you clarify if a dual fuel system can provide heating and or cooling simultaneously for a multi-unit building, for example, a triplex?
No, the dual fuel systems cannot simultaneously, as a single system, provide heating and cooling. That would be similar to going up and down. Same time, you need one of 2 things. You need individual units, or you need a commercial 3-phase type of system with at least dual or multiple compressors in them that siphon off of each other and that kind of stuff. They exist. They're out there, but it's mostly in the commercial world. But yeah, the dual fuel system can't do both heating and cooling at the same time.
Great, thanks. Folks, we have another few minutes on the call here. We're here till 9:30. If you have any other questions, feel free to pop them in the chat or raise your hand. Oh, one more question. Okay, would it be better to have the compressor locked out? This is going back to the discussion around thermostats
Have the compressor locked out?
for dual fuel. Kim, if you want to unmute yourself and clarify your question.
Sorry, I keep bugging you. I was thinking maybe I should just email you. I've worked with heat pumps for the past 20 odd years with our electric company, West Kootenay Power, and then with Fortis BC, we have our dual fuel
Mhm.
rebate, and just that some thermostats, they can change the switchover temperature.
Yeah.
But when the contractor sets up the thermostat, would it be better to get like the compressor lockout, like when they actually set up the thermostat, you can go into more detail, the contractor, and usually they have a passcode and then they go into it, and then they have a lockout temperature so that the gas and a heat pump doesn't come on at the same time to
Yeah,
cause high
that should
pressure.
happen. Yeah, that should happen. Either you configure it to happen,
Okay.
or yeah, it's a default setting, right?
Okay.
Because you do need the heat pump to shut off when the gas
Yeah.
takes over.
Yeah. Because
And
it would,
so having the heat pump shut off is another way. Another way of doing it is locking out the compressor. All that means is
the heat pump won't run with the gas furnace at
yeah,
a certain temperature.
yeah, exactly. The gas furnace is saying, okay, thank you. I'm going to take over from here.
Right.
Right.
So yeah, like one of our things in our rebates is that in order to get the dual fuel rebate, the heat pump has to run for your heating to a certain degree.
Yeah.
And some of the controls I see, like some of them are disabled the thing. So I just wondered if there was a certain way that we could make sure.
Well, you bring up a good point, is that if it's locked out completely, if it's just locked out, not based on outdoor temperature, then all you have is a gas furnace, right?
Right.
Um, it has to be at some temperature. Now, I believe Fortis says 5 degrees.
Yeah, for
Right?
the lower mainland and 2 for
Yeah.
the interior, which
Yeah.
I'm in. But I just wondered if there was a way we would know if they set them properly, because even the balance point doesn't, like the customer can change or the homeowner can change the balance point,
Yeah.
but
Yeah.
in the back end, I think there's a more sophisticated way.
Yeah, well, it depends on the equipment, but
Right,
in
right,
almost all equipment, you have one or two choices. Most North American equipment, the default is you tell the equipment there's a heat pump and it will lock out the compressor when the furnace comes on.
okay,
Why and whenever it comes on.
right,
All
right,
it
right,
needs to know, furnace is on, okay, compressor is offline.
right,
That's the North American manufacturer's kind of default setting. With the others like Mitsubishi, Daikin, um, those types of equipment, that class of equipment, that uh, because they're not traditionally equipment that has dual fuel,
right,
you have to actually configure them. You have to set it up. It's
right.
the default setting.
Okay, 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 got it. Okay, okay. I'm just wondering, I'm just thinking about if we got a photo of the thermostat when they set it up, the contractor, but that's
That
good,
would be,
good
you know
info.
what? I'm glad you brought that up, because that is part of what we're going to be talking about.
Oh,
Commission,
good. Okay,
right? Is what's going on? What's the and what needs to be transparent? What's the reports? What's on the reports?
right.
How do we know what got set up?
Yeah,
That
because
all that stuff, yeah.
yeah, years ago we gave out rebates for hybrid, but the thermostats were more like simple, so it you could tell right away. But then at that time, gas was more money than electric.
Yeah.
So yeah, I'm just wondering if there was an easier way to figure that out without. yeah, but you gave me good information. Thank you so much.
Thanks.
Perfect. Thanks so much, Kim. And that brings us perfectly to 9:30. So thanks so much, Rob, for spending these 90 minutes with us and sharing your wisdom and knowledge. Folks, I did just put the link again in the chat to part 2 of the webinar, and you can expect a follow-up email from me early next week with Rob's slides. And yeah, that's it from us. So enjoy the rest of your day, and thanks for joining us.
Thanks everybody. Take care.